Okay, all good. Tri, I think we can kick it off.
Yeah, thank you, Aleksa, for the kind introduction, and yeah, thanks very much, everyone, for coming here. I'm excited to talk about some of my research on flash attention and other extensions. More recent work, things like flash attention 2, and hopefully give some of the kind of behind the scene insights into how these things came into fruition, what kind of people we collaborated with, and so. More generally, I'm going to talk about kind of the general direction of machine learning in systems. So this is the area that I've been interested in for a long time. And we've seen a lot of promising results, especially recently in machine learning systems that I'd love to share with you. And so feel free to stop me, interrupt me, and ask questions. This is a somewhat, pretty informal talk. Yeah, so feel free to stop and ask questions.
Just a quick note on my side. If anybody wants to ask a question, please raise your hand just to allow the moderation. Otherwise, people will just start jumping, interrupting, so it's kind of hard to moderate. So please just raise the hand, and then we can ask.
Okay, yeah. So let me get started. So I'll start with some kind of high-level motivation of machine learning systems and efficiency and so on, and why I care about this stuff and why a lot of people care about this stuff. So just to motivate, I think most of us have seen that in the past couple of years, machine learning has made exciting progress. And now we call these things AI. So there's been a bunch of tasks or problems that we thought were really hard just a couple of years ago that now these machine learning systems or AI systems can do. As an example, they can help you fix bugs. So you can go on ChatGPT, GPT-4, and you can paste some snippet of code and ask it, what is the bug? How do you fix it? And a lot of times they can actually help you fix the bugs and explain why there was a bug or what is the fix, right? And in another domain, in computer vision, these models can now generate art. So this is actually my first attempt at generating pictures with Stable Diffusion. And I type in some prompts, and it took a couple seconds, but it does a pretty decent job. And this was generated, I guess, a couple months ago, and now we have a bunch of better models now. In other domains, so DeepMind has done amazing work with AlphaFold and AlphaFold 2, and they can use machine learning to predict protein structures really well. As a result, lots of companies are now using this to accelerate drug design. So what we want to understand at a high level is what enabled these advances, what are some of the outstanding problems, and how to approach these outstanding problems. And one line of thinking has been that is scale that has brought quality and capabilities. And we've seen this in the past 4 or 5 years or so, going from BERT large at 340 million parameters back in 2018, and in just 5 years or so, we're getting models at the size of 500 billion parameters with Megatron Turing and Palm, and GPT-4 is rumored to have, I don't know, trillions of parameters. So we've seen that when you increase in scale, you tend to have better quality on existing benchmark. But what's really exciting is that it seems to bring new capabilities. So here's an example. I'm sure a lot of you have played with these language models. I'm just trying to get them to explain jokes. So the input I type in, can you explain this joke? I try 10,000 random restarts of my neural network, but I was accused of overfitting. I guess no good seed goes unpunished. And so I tried this with a 1.3 billion parameter model, and it didn't understand the joke. When I asked it to explain, it essentially just repeats the punchline. It didn't understand the joke. But when I tried with a 175B model, it understands the joke. It understands there's a pun with no good deed goes unpunished. So this is amazing, right? Scale is now more closely tied to advances in machine learning than ever before. And so with scale comes a core challenge, which is efficiency. We have lots of large models that do really well in terms of accuracy and quality, but they tend to be relatively slow we also have smaller and faster models, but they tend to do not as well. So is it possible to get to the point where we have make these models much smaller and much faster to make it easy to train and deploy them, and more importantly, to facilitate research and understanding into what they're doing? Because a lot of times the bottleneck in research is essentially how often you can try things, how often can you run experiments. So that's one reason why efficiency is important. It helps with training, deployment, and research. The other reason is that efficiency can unlock new capabilities. So here's an example. I'm using ChatGPT. I'm asking it to write a 4,000-word essay on the best ice cream flavor. And it was not able to do so simply because it couldn't process anything longer than 4,000 tokens. And now more recently, they've updated, they have a version with 64K, I think, and GPT-4 can go up to 32K. Thanks to some of the advances that we made in the past year or so. So with efficiency, I'll argue that the problem with long context, part of the problem is that you couldn't train these things efficiently with long context. But with advances in machine learning systems, now some of that is possible. So to recap, we care about efficiency because we want to make training, deployment, and research easy, and efficiency could unlock new capabilities. So that's the motivation why I care about efficiency. So my approach to efficiency has been to both understand the algorithms and the systems they run on. So on one hand, I spent a bunch of time playing with fundamental algorithms, trying to understand them. So things like fast matrix vector multiply, I did a bunch of work on understanding exactly what kind of matrices would have theoretically fast matrix multiply algorithm, and understanding things like the attention mechanism, which we all know and love. So that's on the algorithm side. And on the system side, I also want to understand the hardware accelerators and the distributed systems that these things run on. So understanding how GPUs or TPUs are block-oriented devices, and that has a bunch of implications in terms of what kind of algorithms would run efficiently on these things. And in the distributed system, they might have asymmetric memory hierarchy. How can we use these things for the purpose of efficiency? So that's been my approach. So for the purpose of this talk, I'll just focus on one main idea, which is hardware-aware algorithms. That just means that can we design algorithms that take advantage of the hardware that we run on? So one idea, one example is I/O awareness, where we want to reduce reads and writes to GPU memory. And flash attention is an example of that, where by reducing reads and writes to memory, turns out we can get significant speed up on the order of now it's like 5 to 9x. So I'll talk about how we can get, for example, flash attention to be fast, to be memory efficient. And the nice thing is we don't do any approximation, so we compute the same answer. So it's a kind of drop-in replacement. And so we've been very lucky to have our research being adopted by the community. So folks at PyTorch, it's in PyTorch now. Folks at OpenAI, they re-implemented it in Triton. Folks at a bunch of other companies are using it to train language models and foundation models and so on. So now we've seen adoption in some of the areas that I mentioned before. So in text generation, a bunch of language models are trained with flash attention. So Llama from Meta, Falcon from TII, MPT from Mosaic, and other language models. In image generation, so Stable Diffusion has trained with flash attention and has flash attention in inference. And for drug discovery, well, DeepMind's AlphaFold 2 was before we did flash attention, but there are a bunch of open source alternatives like OpenFold and Unifold, which use flash attention for to make training and inference faster. So that's kind of the overview, and now I'll go into a little bit of details about flash attention, how attention is bottlenecked by memory reads and writes, how some of the techniques we use, like tiling and recomputation, can reduce reads and writes, and some of the applications where we can train transformer faster, or with longer context we can get better transformers. Okay, so and then in the end, if I have time, I'll go into some of the future directions. That could be a chat as well. So I'll just digress a little bit and talk about behind the scene, how we came up with flash attention. And of course, flash attention was done with my co-authors, Dan Fu, Stefano Erman, Atri Rudra, and Chris Ray. And so it started out actually, which is me playing with MLPerf code. So MLPerf is this kind of industry-wide machine learning training benchmark, and it's been around. It started as GonBench from I think folks from Stanford. Then the industry folks kind of come together and say, hey, let's do a kind of industry-wide version of this. That became MLPerf, and I think in 2019. And so my advisor Chris, he calls it kind of the Olympics of machine learning performance, where folks from NVIDIA, Google, Microsoft, and so on come together and try to benchmark their machine learning systems. So they usually the one example is, okay, how fast can you train a ResNet to whatever accuracy, and on whatever device you choose, right? For example, NVIDIA has done an amazing job there. They spend quite a bit of effort trying to make the systems as fast as possible. So this is kind of the Olympics of machine learning performance. And so I was doing a previous project back early in 2020, early last year, and so we were touching on machine learning performance. At that point, I didn't understand too much, and so Chris told me, "Hey, you're looking at machine learning performance. Why don't you go compare to MLPerf, because those people know what they're talking about, right? Those are the experts, right?" And so that was very wise advice from Chris. And so I started looking at MLPerf code, in particular the BERT implementation from NVIDIA. So I was reading just the attention code, the attention implementation from Youngjin Ko. So he's an engineer at NVIDIA. So the code is public, by the way. Yeah, it's in Apex. So I looked at it for a couple of days and I'm like, wow, this code is amazing. So I just sent him an email saying like, hey, I read your code and I liked it. So that's it. And of course he's pretty happy. And I thought more and more about it, and I realized that, hey, this code is amazing, but it's only worked for BERT, so it worked for sequence length 512. It worked on A100 only. It worked for head dimension 64. So I thought, hey, we can make it much better by combining a bunch of ideas that are already in the literature. Of course, it takes a lot of some effort to combine these ideas. So things like the online softmax trick from folks from NVIDIA who wrote a paper in 2018. Folks from Google, Robin and Slot, wrote a paper late 2021 on using online softmax for attention, which allows you to break the computation up. And we use tiling, which is a very classical technique to do computation by blocks. This is probably back in the 1970s. And recomputation, which also a classical idea. So I saw that, hey, we can combine some of the ideas from both on the system side, tiling, recomputation, really, fuse kernel from starting with the code from Youngchen, with a bunch of other ideas from the machine learning side, things like online softmax and so on. And that turned out to work pretty well. Yeah, of course, it took several months of just coding in CUDA to get these things to work. But in the end, we managed to get it to work. So that's kind of the behind the scene. I'll pause here. It seems like there's been some questions on the chat, so I'll pause here to see if there are questions, and then before proceeding.
I think I can reply to all of them, but maybe I had one question. I see that the email is dated to like February of 2022, and Flash Attention came out like last summer, so that's a couple of months
Yes.
after this email was written. So that means, like, how long were you actually working deeply on this problem? Was it like only a couple of months? When I say a couple, like 3 or 4 months, or more than that?
So we released it end of May. The code was also released end of May. I think the paper was submitted to NeurIPS, closer to end of May. MLPerf that year, which we participated in with flash attention, was I think May 19 or something. So it was like about three months of work, just implementing things. I think implementing things was like 2 months, and then writing papers, running experiments. Of course, is a bunch of us, like, co-authors with Dan, Sapno, Atri, and Chris as well.
It's crazy just how much you managed to squeeze out in a couple of months, like a couple of students, and it's just respect.
And of course, I think there's a line of like in the chat of like sending emails like this. Sending emails like actually Chris encouraged us to send emails like this, and as researcher, like we feel really good about if someone to send emails like, hey, I read your paper, I think it's it's good, it's cool, I like this aspect. So Chris, my advisor, encouraged us to do this kind of as a habit, and I also start doing that, and people seem pretty happy, and you don't, it's just like a couple lines, and you make people happy. All right, so I'll proceed. That's kind of the behind the scene for flash attention. For flash attention 2, I'll do another behind the scene later on as well. Okay, what was the motivation for flash attention? So one direction we've been pushing on for several years now is to model long sequences. So as I mentioned, these are kind of new capabilities of machine learning models that we want these models to have. So why do we want to model long sequences? So one is we want to enable new capabilities. So in NLP, we need large context to understand books and plays and understand code bases. In computer vision, we want to close the reality gap. So we want to model images of higher resolution with that usually gives us more robust insight, and higher resolution usually translates to long sequences if you use things like vision transformer. And it could open new areas. So in time series, audio, video, medical imaging, data naturally is modeled as sequences of millions of steps. So here's an example of slides of medical imaging in histopathology. They're trying to segment or detect cancer cells or tumors. And in that field, they never downsample the images, simply because once you downsample, you lose the details that allows you to detect cancer cells. So the images are extremely high resolution, and that leads to sequence length of up to millions of patches. So we see that long sequences could either get its new capabilities or close reality gap or open new areas. And I would argue that efficiency is one of the bottlenecks to model long sequences, especially with attention, which is now kind of the core is now the core building block of the dominant architecture, which is transformer. And here I'm using context length to mean we're doing sequence modeling. So context length just mean how many other elements in the sequence does the current element interact with. And here's an example. Naively, what if we just increase the context length? And so if I take Megatron LM, this is back in last year, where we're trying to train, I think this is a 1.3 billion parameter model or 2.7 billion parameter model, and I'm measuring training speed, which you can think of as proportional to how many tokens you can process per second. And at 2K context length, it does a pretty decent job. If you're familiar with things like model flops utilization, this is around 50% utilization, which is pretty good at the 2K. But if you increase the context length to 8K, then it either significantly slows down. This is already tokens per second. It significantly slows down, or it goes out of memory and you can't train at all. So we see that this is an efficiency problem. We could increase context length, just that we can't, or we couldn't train these things efficiently, or with, or we don't have enough memory to train these things. So we see that it slows down by 2x. So how do we efficiently scale models to long sequences? And so I'll go a little bit in terms of background, in terms of model architecture. I know most of you are familiar, so I'm just so that we're on the same page in terms of terminologies. For the transformer, there are a bunch of encoder blocks, and each block has two main layers, the attention layer and the MLP layer. And if you want to scale to long context length, the MLP layer is relatively straightforward to scale because they just process the tokens independently. But the attention layer is the one that makes it hard to scale, and I'll mention why. So just a little bit of background on attention. I'm sure a lot of you are familiar, just so that we're using the same terminology. So as input, we have the query Q and the K, the key K, and they're of size n by d, where n is the sequence length on the order of 1K to 8K, and the d is the head dimension, which is 64 over 128. You multiply both of them to get some kind of similarity score of size n by n. You take the softmax, which is this attention probability, and just a reminder, softmax, what you do is you exponentiate everything, and then you divide by the sum so that everything sums to 1 and is positive. So it looks like a probability distribution. Then you take that softmax and multiply with the value, which is also provided. And you end up with the output, which is of size n by d. So that's the recap. We see that attention scales quadratically in sequence length n. Simply because, for example, we are dealing with these matrices of size n by n. So just reading, writing them, or doing any kind of computation on them will take quadratic time. Ever since attention got popular in 2017, lots and lots of folks have been trying to make attention more efficient. And a lot of focus is to approximate attention. So there's been, I think, two main classes of approaches. So you either use some kind of sparsity. You say, instead of computing full attention, I'm only going to compute attention with respect to some of the entries. Or you use low rank factorization, which says that I'm going to assume that the attention matrix has some kind of low rank structure, and that allows you to do to approximate attention and hopefully trade off quality for speed. So you might suffer and you might lose in quality, but hopefully you would go faster. And I've worked on this as well. I've written several papers on attention approximation. But it turns out when we talk to practitioners, they say, well, these methods don't really go faster in wall clock time. Horace gave a talk, I guess earlier this week, about flops might not necessarily correlate with runtime. So practitioners, they told us, hey, these methods, they trade off quality, but they're actually not faster. So these methods haven't been widely adopted. So this motivated us to figure out if there's a fast, memory efficient, and exact attention algorithm, and there's a way to get there. So the main observation is that we noticed that attention is bottlenecked by memory read and write. It's not so much bottlenecked by computation. So just the two intermediate matrices, S and A, they have size n by n, and it turns out just reading and writing them to GPU memory takes the majority of the time, even though they essentially have very little very few floating point operations. So yeah, the biggest cost is in moving the bits, and a standard implementation will require repeated read and write to slow GPU memory. So that's the observation. So in order to tackle this bottleneck, we just need to understand the hardware a little bit. And Horace Horace, he wrote a great blog post on this. Like I think to this blog post anytime people ask for, how do I start understanding this kind of things? His blog post is excellent. So I would highly recommend his blog post, Making Deep Learning Go Brr from First Principle. And I know he gave a talk earlier, was it yesterday or earlier this week? So here's a brief recap. You should go read his blog post. So here's a kind of model of what a GPU look like. So they have HBM, which you can think of as GPU memory, and they have these compute units and SRAM. Compute units is the actual hardware unit that does the computation, and SRAM you can think of as a small cache close to the compute unit. If you're familiar with the CPU architecture, then you usually have a large amount of RAM, and then next to the CPU, you have like L1 cache and L2 cache and things like that. So similarly to the GPU, you have HBM, which is GPU memory. You have the SRAM, which acts like a cache for the computation. And there's a huge difference between the two kinds of memory. So for SRAM, it's usually like 3 orders of magnitude smaller, but an order of magnitude faster. Similar to in CPU is DRAM and cache. Cache is usually much smaller but much faster. And so the way things work is that the inputs start out in HBM, in GPU memory, and it needs to be transferred to the compute unit and SRAM for computation. And then in the end, you do the computation and you write the output back to HBM. So the question is, can we exploit the memory asymmetry to get speed up? And the answer is yes. So if we design algorithms to be IO aware, if we account for reads and writes to different levels of memory, we can exploit this asymmetry. And so one classical technique to reduce memory reads and writes is to compute by blocks, also known as tiling. And there's several challenges with this when you apply it to attention. One challenge is that if you compute the softmax normalization, naively, you would need the entire row of the input to compute softmax, so it makes it hard to compute things by block. And number two, the backward pass, if you want to compute gradient, you need a large attention matrix from the forward pass to compute the backward gradient. And so we use some of the classical techniques to address these things. So tiling, which means restructure the algorithm to load block by block from HBM to SRAM to compute attention. You need to combine this with this online softmax trick, which people have been writing about for several years. And for the backward pass, you can do recomputation. It turns out you don't need to store the attention from the forward pass. You can recompute in the backward pass. And surprisingly, that's faster. So I'll go into a little bit of, so I'll skip some of the detail explanation. So I'll just give maybe more high-level overview of how the computation proceeds. And Aleksa just wrote an excellent blog post, like going through all the details of how to do softmax rescaling and so on. So I highly recommend that as well. So for tiling, you want to break the computation up into blocks, and then you're going to compute block by block. You need to do a little bit of rescaling to get the right answer, but you will get the right answer. So here's the overview. So you load inputs block by block from HBM to SRAM, and then on chip you compute attention with respect to that block, and you update the output in HBM by scaling. So here's an animation. Thanks credit to Francisco Massa, who made this animation. So I'm showing the queries on the left, the keys are at the top, the values on the right, and the outputs are on the right. And conceptually, we operating block by block, but we don't write down this big matrix n by n in the middle. So here's how we proceed. So we move from left to right, and then. So I don't know how well it shows up on Google Meet. I don't know if the animation actually showed up. That's fine. If you didn't get that, that's fine. Okay, so there is some. So I'll pause here for questions.
I don't think we have one that's related to one of your previous slides. Okay. If it's not too out of context for you, yeah. Like you mentioned you needed like roughly 2 months to code up stuff and a couple more months to write a paper. Summary tasks regarding that period. What's the time when you really started going deep into the MLSys, into the whole, I guess, coding and CUDA stuff?
So I started learning CUDA back in 2020, and it was for a strange reason. So we wrote a paper called butterfly factorization. Doesn't matter what it is a way to, like, there's a special class of matrices that theoretically are very nice, and they have fast multiplication algorithm, and on the order of n log n. So instead of n squared, if you have the special class, the multiplication is on the order of n log n. And the intuition is they kind of look like fast Fourier transform. If you're coming from kind of signal processing background, you understand fast Fourier transform, very similar. So on the theory side, it's beautiful. There's a lot of elegant result that about butterfly matrices that some of them we prove. But when we actually run it and we implement it in PyTorch, or back then when I implemented it in PyTorch, it was really, really slow. It's like much slower than just a standard matrix multiply. And so I'm like, hey, these matrices are so nice. I want to show people that you can actually get speed up from butterfly matrices. And back then, for some reason, I spent a couple months just like learning CUDA and implementing butterfly matrices. So that was fun. I didn't think it would be useful later on, but turns out it ended up being useful later on. So I would say that's when I started learning CUDA. But I didn't really dive deep into machine learning system until I guess 2021. We started thinking about sparsity, and we wanted to, on the theory side, things are very nice, but on the kind of, we were motivated when we talk about practitioner. They're like, yeah, these things are great in theory, but in practice, they're still pretty slow. They don't actually get wall clock speed up. So that's when I started wanting to understand, like, why don't they get, in theory, why they're so nice? Because I come from more of a theory background. They're so nice. I want them to work. And that requires understanding a bunch of ideas from the system side that I didn't understand. Things like, block computation, memory, reads and writes, and things like that. So I would say, I started getting to it in 2021, which is pretty. Also somewhat recent. Of course, there's been folks doing machine learning systems for a while. Yeah, so hopefully, okay, that was a long answer to the question.
No, I really loved it. I think people want to hear these, because I guess most people aspire to do something similar, and so like just understanding that the background stuff that you cannot read in the paper is super valuable.
For sure.
You can continue.
Yeah. So let's continue. I'll mention some of the high-level ideas. I won't go into too much detail. So one idea was tiling and combining with the online softmax to do computation, to do rescaling. The other idea was for the backward pass, which is recomputation. We don't want to store these big matrices, the score and the attention, which upsize n by n, because they would just either, one, they require too much memory, and two, just writing these matrices actually take a long time. They take the majority of the time. So the answer is simple. We just recompute them in the backward pass. And once you have these QKV loaded into SRAM, computation is actually pretty cheap. So this is something that you build intuition about what's fast and what's slow. And so, somewhat counterintuitively, because even though we do more computation, but as long as we reduce memory reads and writes, we can get significant speed up. So here's a comparison between standard attention and flash attention. So in terms of number of flops, we incur, like in this case, 13% more flops. But in terms of reads and writes, we reduce by 9x, and as a result, we can be 6x faster. So this is somewhat counterintuitive, but once you understand the hardware and once you understand the bottlenecks, then it would make more sense that somehow computation in a lot of cases is cheap and memory I/O is expensive. So yeah, we can speed up the backpass even with increased flops. And so the high-level result for flash attention was that we had 2 to 4x speed up compared to optimized baseline, and we get 10 to 20x memory reduction with no approximation. So memory is now linear in sequence length instead of quadratic. So that allows you to at least train with long sequences. It would run, and long sequences, we also get 2 to 4x speed up. So okay, how does that play into the motivation, which is we want to train models with longer context to get new capabilities and so on. So here's an example I showed with Megatron LM back then. When we increase context length, we slow down number of tokens per second slow down by like 2x or run out of memory. So with flash attention, you can still get pretty fast training speed. So you get something like we were at 170 teraflops per second, 175 teraflops per second, and we don't run out of memory. So that allows us to train models with longer context, for example, 8K context, and we see that by training models with longer context, we get better models. So in terms of upstream quality, like validation complexity, we get better numbers. And in terms of downstream, here's an example of this task called chapter break, where given the end of a chapter, can you predict the next chapter of the book? And so we see that as we increase the sequence length, the model generally does better at this particular task. So we see that flash attention can speed up training by around 2x or up to 2x, and we can increase context length by maybe 4x and improve model quality. And as a result, I think lots of folks have been using it to train models, and model context length has been increasing recently. So that's kind of some of the highlights from flash attention. And then I'll mention just a couple ideas from Flash Attention 2, which is this recent work, which we released it on Monday. So Flash Attention, even though it was already 2 to 4x faster than the optimized baseline, there was still quite a bit of headroom. And here, so for example, the highlight results is that we're about 2x faster in wall clock time. And the key ideas here are we want to reduce non-matmul flops. So it turns out matmul flops are cheap because hardware has really specialized compute units to do matrix multiply. So everything else is like much slower in comparison. And so we reformulated the algorithm a little bit to reduce these non-matrix multiply flops while still getting the same result. The second idea is to parallelize over a sequence length dimension to improve occupancy. In many cases where the batch size or number of heads is really small, we weren't really using all of the GPU resources. So by parallelizing more, we have more work so that more of the GPUs could be used. And we do better work partitioning between warps. Warps is a unit of 32 threads. So this is a little bit of low-level optimization to reduce communication between warps, and taken together, they improve speed by around 2x, and it's getting somewhat close to, I would say, the upper bound, which is how fast can just pure matrix multiply go. So we're not quite there yet. Matrix multiply can get you 80 to 90% of the theoretical max. Flash attention right now could get to 60 to 70%. So there's still a little bit of headroom for A100. For H100, there's quite a lot of work we want to do next. The new hardware features that we want to take advantage as well. So the upside here is we get 2x faster wall clock time. We can train model with 2x context length for the same cost. So just a little bit behind the scene. So Flash Attention 2 was actually started as a refactor of the code base to use CUTLASS 3, and I can't say enough good things about CUTLASS. The team has put out, the NVIDIA team has put out an amazing library, especially CUTLASS 3, and they've been extremely supportive. So it started out, I think CUTLASS 3 was released in late January, and I wanted to play with it. So I'm like, okay, I'm going to use this as an excuse to play with CUTLASS 3. I'm just going to refactor my code to use CUTLASS 3, which they provide these primitives to do matrix multiply, memory loading, and so on. And I wanted to play with it. So this was back in late January. I started playing with it, and it has it's a result of exchange of ideas between different Flash Attention implementations. So the credit here goes to Phil Tillett from OpenAI. He implemented Flash Attention in Triton, and Daniel Haziza from Meta, he implemented Flash Attention in XFormers. And we talked a bunch and kind of exchanged ideas about how things could be better. And his benefit from conversations with a large number of folks, Phil Wang, also known as Lucid Brain, Marcus Rabe, James Bradbury, Yangchen, he's the OG. He implemented the FMHA. Julian, Daniel, Michael, Horace, Ashish, Eric, and a bunch of folks. Dan and Chris has been very supportive and encouraging. So credit to these folks, and of course the compute support from Stanford NLP and Stanford Center for Foundation Models. So that's kind of the behind the scene. It was written on and off for over several months. Started as an excuse for me to play with CUTLASS 3, but ended up, I discovered a bunch of ways that we can improve things, and of course exchange of ideas between different folks. So that was kind of the behind the scene of Flash Attention 2. I'll pause it to see if there are questions.
Yeah, there are many questions in the chat. Maybe does anybody want to ask a question themselves, or you want me to read it? Luca, you want to ask a question? Yeah, go ahead.
Yeah, hi. So these results really do look impressive. And what do you expect? Like, how much time will it take for Flash attention to become default implementation in popular frameworks? Like, so that people start using it without even knowing that they're using it.
Right. Yeah. So I think so the PyTorch team has done a great job integrating it. So in particular, Dries Jesus, he integrated it into PyTorch, or at least Flash attention v1. For v2, we're doing a little more testing. There's some edge cases. People sending bug reports, which is great. Yeah, I'm trying to fix them. We'll take a little bit of time to get it to be stable, and then hopefully we'll be in PyTorch in the next couple of months. I don't know what I haven't really checked what their release schedule is. Of course, like I think Flash attention is quite fast, but it has certain limitations. You know, in terms of head dimension, it only works for let's say somewhat newer GPUs. So is you know, there's some effort of collaborating with folks to, for example, making it work for other kinds of devices, or support more data types and things like that. So there's still a lot of work. I think we kind of target because it's more of a kind of proof of concept, kind of more researchy. Like we're not doing, or like for my part, like I wasn't thinking of like, here's a product that like will cover all the use cases. It was more like, hey, here's a proof of concept. We target these core use cases, like, you know, language model training, and we show that hey, these ideas are useful. That's like coming more from a like academic background, and of course there's still a lot more work to make sure that it's, you know, well supported, it's robust, and so on. And there are cases where Flash attention might not be that well suited if you're playing around with things. Like if you want to change, hey, I want to do this variant of attention, like where, you know, let's say you add this thing to the attention, or like apply layer norm to the attention because before doing such and such. The PyTorch is still great at that. You know, it's great to experiment. Flash attention is more, it's like kind of optimized for the core operation, which is attention. If you want to change things, or you want to play around with ideas, it's not quite so easy. But things are changing. Filterlet has been implemented in Triton. Triton, I also you know, very much supportive of Triton. Triton make it easy to, you know, play around with things. So maybe we'll get to the point where, hopefully, we can get to the point where you can essentially write PyTorch code and express some of these ideas, and then compilers or code generation generate code and get really efficient code. So I don't know what the final form would look like. Is it just like, here's optimized subroutine to do attention, or is it like, hey, we put these techniques in compilers that you can still write PyTorch code but generate really efficient code? I don't know what the final form would look like, and of course, you know, we're pushing on both directions.
Awesome reply. Maybe a quick question is, do you expect the V2 to have any, like, for people to have more difficulties implementing it compared to V1 for whatever reason?
So V2, I think some of the ideas, for example, Filterlet kind of, you know, it took him a couple hours to implement some of the ideas. So, you know, some of the ideas are relatively simple. Some of the ideas are a little bit harder to implement, and, you know, it just takes time and effort. Hopefully in the next couple months or so, for example, the Triton implementation will be faster and be on par with the CUDA implementation, so that people can easily play with that. So Filterlet is doing an excellent job there with Triton. Yeah, I'll mention just a couple of future directions, and I'm happy to stick around and answer questions as well.
Awesome.
So for future work, yeah, personally, I'm excited about software hardware co-design and long context for new workflow. So on the software hardware co-design, this is more of a research direction. So we see that right now we have models and hardware that are quite well optimized together. You know, if you run transformer, standard transformer on GPUs, that tends to be quite optimized. But if, as a researcher, if you try some crazy ideas or something like that, you will probably be 5x slower than you should be. The goal is we want to get to the point where kind of the entire stack is much more flexible and much more optimized. So you know, working with folks from PyTorch, OpenAI, NVIDIA to have this kind of full stack of, you know, both smart compiler and runtime, it's gonna, for future work, it's gonna involve a bunch of new ideas like sparse matrix multiplication, data flow architecture. Going to require working with a bunch of folks in machine learning architecture, programming languages, compiler, HPC, and network, and so on. So I think this area of machine learning systems, and in particular this direction of software hardware co-design, is very exciting, and we're seeing more and more motivation for this. So that's more on the system side. On the AI side, I'm still excited about long context, especially for new workflows that are more interactive. So now, if you're chatting with using ChatGPT or GPT-4, these things have much longer context, and you want to go back and forth with them. That means that the models need to incorporate much longer context from user history. And we've seen that GPT-4 has increased context from to 8K and 32K. So here's a fun example. So some folks from Chris Lab, he put out this demo called ChatBCG, where you can type some prompts and it will generate PowerPoints for you. So it's going to require a bunch of interactions between the model and the user. And well, this my PowerPoint wasn't automatically generated, but maybe in the future that could happen. Or the folks at the Depth, which are a bunch of my friends, they're building systems that can automate a bunch of tasks for you, and again that's going to require interaction with user giving feedback, going back and forth. The model needs to understand user preferences and history and so on. So I think on the AI side, these applications will be more and more popular, and there's more needs for long context. On the AI side, how do we effectively model long context? How do we make it efficient? I think that's still in a direction that I'm excited about. So that's kind of some of the future research direction I'm excited about. And then I'll pause here. I know we're a little bit over time, so I'll pause here. Happy to stick around and answer questions. And yeah, thanks so much for your attention.
Thanks a lot, Creep. And as far as I'm concerned, I'm not sure about the folks. If you have anything more slides, you can keep on presenting. As far as I'm concerned, if that's fine, or we can go to the question answering section / community hangout.
Yeah, so I'm happy to hang out. I think hopefully some of the ideas, high level ideas, are there, and yeah, happy to chat. Awesome.
Maybe I have one question. You mentioned the coevolution of hardware and algorithms. Like, is there any particular hardware company that you're currently bullish on, like closely tracking what they are doing? Yeah.
From my perspective, like I'm focusing more on like AI research. So better hardware will lead to better research. NVIDIA has done a phenomenal job. So everyone knows that NVIDIA is kind of the most popular GPUs right now. Of course, the AMD folks, I think, have also implemented versions of flash attention. So the ideas are getting more popular. I think one hardware company that I have some friends there is Salmonova. I talked to folks there simply because some of the folks there were from Stanford. So I don't understand enough about hardware. I'm definitely not a hardware person. I think it's great that there are these newer approaches to hardware. And it remains to be seen whether how the scene will play out. But I'm personally not a hardware expert. My perspective is kind of may the best hardware win. And of course, we work with folks from, for example, the CUTLASS team has been very supportive.
Somebody asked, a question in the chat: how much energy consumption in direct computation during backward pass compared to the standard implementation? I guess that's just related to how much operations you have or whatnot. Like, I don't know. Yeah. Do you think in terms of energy?
Yeah, so that's a great question. I personally am not familiar with energy. My understanding, which is my rough understanding, is that computation, which happens close to the chip, is relatively cheap energy-wise, but memory reads and writes, which means you have to transfer between, let's say, off-chip memory like HBM to on-chip to process. Memory transfer is usually expensive, like 10 or 100x more expensive than doing a floating point computation. I might be off by an order of magnitude, I don't know. But my understanding is that memory transfer, memory reads and writes are actually quite expensive in terms of memory. So reading from far off chip, like far off memory like HBM, and transferring to to compute unit is like 10 or 100x more expensive than reading from, let's say, SRAM or registers. So I think by reducing memory IOs, you actually do get better energy efficiency. But the caveat is I'm not an expert in this, so that is my impression.
Chris, go ahead.
Hi, Tri. Thanks for your presentation. There was a archive paper a couple months ago about basically splitting context, kind of doing a pre-organization. I think before it got to the transformer, but it basically categorized everything so that when it was kind of like a semantic search. What it would do in a semantic search initially to reach for context, it would go into like one of like 16 or 32 areas, and then it would pull from there. I was wondering if you saw that and what you thought about that for future direction. I think that's being used for similar models that get up to like 100,000 contexts, stuff like that.
Yeah. So if you can post a link, that would be helpful. I'm personally not familiar with this particular paper. I think retrieval or some kind of sparsity has been pretty useful for long context. So maybe for super long context, you can't do full attention. You can do some kind of sparsity or retrieval and things like that. I think that's a promising direction, and I've heard from friends that some of the companies are experimenting with this. I think right now there are a bunch of approaches for long context. One is for flash attention, which is like, hey, just do dense attention. Can we make that hardware friendly? Two, some kind of sparsity. So flash attention is quite compatible with things like block sparsity. So you can also exploit that. The third one is more retrieval based with like vector database and so on. And the fourth is like a completely different architecture. So things like recurrent neural nets, where it essentially compress the previous history into a fixed size vector. So I think all those all these approaches are promising. Maybe nothing has really emerged yet as like the canonical kind of next the right thing to do. I personally am excited about recurrent neural nets. I've written a few papers on things like state space models, which can be viewed as recurrent neural nets. That's my personal opinion. That's something I'm excited about. So for example, other folks like have done RWKV, where they show that RNNs can actually be quite competitive with transformer at scale. And so I think with RNNs you can get a lot of benefit for inference throughput. So because you don't have to keep around the entire history, you compress everything into a fixed size a state vector. You can, I think, potentially get much higher inference throughput. Of course, a lot of work still needs to be done. And on the transformer side, for inference, we can still do things like MQA and group query attention and so on, and quantization, which also helps with memory. So it's unclear what kind of approaches would win out. I think right now it's probably people are experimenting with things, combining things like retrieval and block sparsity and so on. So it's an exciting time. I know the open source community is like building on this stuff very, very rapidly. So hopefully we'll see a lot of progress in the near future.
Definitely. Talking about RNNs, did you see the I think yesterday the retentive network paper came out?
Right.
And
right.
Did you see it?
Yes.
Yeah, that looks. What's your take on the RetNet? Like they're promising of one like inference and all of the goodies of transformers, plus like obviously apparently they have better like scaling curves, at least to maybe 7 billion from 2 billion onwards. It seems to be better. Like what's your take on this whole new approach? This looks very exciting.
Yeah. So the caveat is I didn't read it carefully. I skimmed it, so I might have missed some of the details. I think RetNet I like the idea of connecting to like recurrent neural nets and so on. You know, I personally am bullish on RNNs, which may be a contrarian position given that I also work a bunch on attention. Yeah, we play both sides. So yeah, the numbers look pretty promising. What I didn't see was like maybe there's hopefully it would make it more convincing is like, hey, we released this model that's like, you know, as good or like better than this public model. That would be quite convincing. So maybe at some point they'll release a model that say, hey, we're better than, I don't know. Maybe Llama is really a high bar, but maybe GP something that's like better than or the same as, and what's the standard for these like PTA or GPDJ or things like that that show, hey, we actually have a pretty competitive results with these public models. So that would make it quite a bit more convincing. So and I think it connects to a bunch of previous models on state spaces that I've worked on, or we'd worked on as well. Things like H3, Hungry Hippos, which I didn't get a chance to talk about today, and Hyena and RWKB. So I think these ideas are starting to people are picking them up, and I think a lot of people are pushing, or not a lot, maybe some number of people are pushing on this RNN direction.
Yeah, I think it's very exciting. Yeah, like to diverge a little bit from the convergence of transformers that happened, although that brought a lot of good things. Chris, I see a very cool question about Mojo. Do you want to ask that question yourself, or I can read it? Okay, so Chris asked, isn't Mojo going to completely transform the software-hardware integration optimization space soon? Like, what's your take on Mojo in general? From Chris Latner, if you're familiar with the work.
Module? Maybe I'm not familiar.
Mojo, like the new language that Chris Latner is trying to optimize, like that has Python-esque type of interface with all of the goodies of C++.
Right. Yeah, Mojo. Yeah. This is from this company Modular AI, right? Yeah, I talked to Chris Latner a while back. Of course, like they have the credibility in terms of compiler. He was the person behind some of the major compilers. So like they are the experts when it comes to compilers. I think the pitch is compelling. The pitch is, hey, these things are going to be deployed on AI models are going to be deployed on different kinds of devices, like phone, CPU, GPU, different kinds of devices. So maybe you want the compiler to do a lot of the work. And I personally, I'm a fan of that philosophy, which is we want more flexibility. We want more so that AI researchers can try out more ideas. I think currently the issue is that performance is so critical that your training runs that costs upwards of millions of dollars. So people are willing to go into really low level details to optimize to get the most efficiency out of their device. So what that means is that as a compiler, I think generally they prefer like more general technique that work across the board and so on. But for efficiency reason, like a lot of work goes into like optimizing for, we're training with like NVIDIA GPU, A100, H100, going through like NVLink and InfiniBand. So we want to exploit these special hardware features. I think for efficiency, these two will come into a little bit of friction where compilers want to be general, but for efficiency reason, some folks will be willing to like just hand tune and hand write a bunch of things. So we'll see. Maybe for some cases where like inference on different kinds of devices and phones and so on, I think Mojo could be promising. Personally, I think in the near future, I would still imagine that people are still running training with like PyTorch or framework like Megatron LM, which are very much optimized for transformer and running on GPUs that are connected with some kind of networking. So in the near future, I still see that maybe a compiler-based approach might not be able to match the efficiency of like something that's hand-tuned, but we'll see. But Chris Latner has a lot of credibility, so I wouldn't put anything past him. Maybe he'll do amazing things.
What do you feel are the most promising approaches to compiler-level performance optimizations? How do you feel about mechanistic kernel search?
So I'm personally not familiar with mechanistic kernel search. I'm also not a compiler person. I talked to some friends who are into compiler. So Phil Tillett, this person, he wrote the Triton. Of course, a bunch of other folks work on Triton as well. I think right now the approach is that the PyTorch team, what they do is they capture the graph. I'm sure Horace talked about this. But PyTorch can capture the graph and then generate code, generate Triton code, and then Triton can then go optimize things. I don't, since I'm not an expert in compiler, I don't know what's the best approach is. So yeah, I'll defer that to maybe experts in compilers.
Nice. I think we can stop recording and maybe open it up for more general questions.